morning. Let us start. So, before we continue, any questions from the last lectures? Everything clear to everybody? Interesting. Okay, yeah. Oh, very good. So this was the last slide here. And we now still have few slides before we go to the uncertainty sources. So why do we need to evaluate measurement uncertainty? Well, first of all, obviously, it is considered these days the main parameter showing you how accurate the result is. Also, you cannot really compare two results if they are without uncertainty. So you cannot say whether they are in agreement or in disagreement. If we go for a moment back, if we would have just 0.8 and 1.2, sorry, yeah, 0.8 and 1.2 without any uncertain information, we might say, hey, wait a minute, they are completely different. No? But if now we have these numbers together with their uncertainty estimates, then we can say, we cannot say that they differ. They're actually indistinguishable. No? So the amount of lead in that water might be just exactly the same. These results do not enable any differentiation between these two waters. I will later on teach you how to compare rigorously, numerically, to measurement results to each other and tell whether they can be considered to be in agreement or in disagreement. Then later on in this course, we will look into traceability, and we see that uncertainty is also a key component of that. Then, if you do careful uncertainty evaluation, then that has the added value that you really think through what you are doing. And that oftentimes might lead to improvements in your method. You might discover, okay, this step gives a lot of uncertainty. Let's see if we can improve it somehow. Make it less contributing to measurement uncertainty. And this is exactly written here. You can get information for improvement. Hommikust rõõm sind näha. So, and few more things. We will see later on that there are some, let's say, formalized approaches to measurement uncertainty evaluation, of which we will learn two here in this course. But even more important than the, let's say, mathematical formalism is the common sense. Yeah? So it is easy to go completely wrong with your uncertainty evaluation, either get tiny uncertainties or huge uncertainties, which are uncertainties pretty much the same magnitude as your result, or sometimes uncertainties bigger than what your result is. So in all such cases, most likely you made some mistakes somewhere. So you have to be able to critically look at your data. This is something we will also look at later on. And also, we will see later on that very often it is the availability of data which tells you which approach to measurement uncertainty evaluation you should use. So measurement uncertainty evaluation can be based on very different kinds of data. And we will see in this course what kind of data you need for one or the other. And now what oftentimes I get asked when I do some training courses or consultations with industry people or people from routine labs, and they say that, hey, wait a minute, we are using a standard method. Yeah, standard method. And the standard tells me what the uncertainty is. So I have a standard, it tells me what the uncertainty is, and they ask, am I right that I don't need to do any measurement uncertainty calculation? Because I have here the standard which tells me what the uncertainty is. I would say that this applies only to very, very standardized procedures, very standardized methods. Clinical analyzers are a pretty good example here. I don't know how much you know, but in clinical chemistry, a lot of the urine analysis, blood analysis is done with such machines which are of the same size as two of these things. People, instrument operators, only load racks. Samples are all in standardized. All of you have been to doctor, you know what they have, what they put into racks, and racks are put into machines. And then reagents are put in some canisters into other slots of the machine. So people simply service the machines, and the machine does everything. So samples go in from the one end and from the other, and analysis results come out. Then there's the company who sold the machine, who comes every now and then, does the maintenance, which everything is exactly prescribed how to do, etc. So yes, I agree. In that kind of analysis, when the humans, for example, are just transport workers, who can carry the things and put the things into the... In that kind of situation, you can really say, okay, the producer gives us this machine and tells us the uncertainties will be this for the different parameters. Then this is what you can do, yes, and you can use those uncertainties. You don't need to do any evaluation of your own. But this is quite rare. I mean, it's not rare in the sense that clinical labs are not rare. But if we now take real analytical chemistry laboratory, environmental or food control, etc., you don't find such machines there. There you will still find usual GCMS instruments, UV visible spectrophotometers, etc., atomic spectroscopy devices, and so on. And with all those, even if you use standard methods, the standard does not know how skillful is the person who is running this, how new are your reagents, how new is the instrument, Then all your glassware and things might influence. Then sample preparation, a big separate topic is sample preparation, where skill is often very important, skill and experience, how you exactly fill things and whether the layer is even and now how fast you add solvent. So there are so many small nuances which are so important, and which all influence measurement uncertainty. So but I would say that in all usual cases, you cannot abstract measurement uncertainty from the working practices of your lab, from your lab conditions, from your instruments, from your instrument conditions, and from the skill of the people that you have in the lab. Meaning, even if it is standard method, standard procedure, you still have to carry out evaluation of measurement. And now, before we go to the uncertainty sources, any questions? Yeah, please. Mm-hmm. Blunder is a big error, so you dropped something on the floor, etc. These are indeed not accounted for. But even if you don't do anything wrong, different level of skill might still lead very different quality of results. Again, I think it is possibly the easiest to explain with sample preparation when you, for example, Okay, you have to condition your solid phase extraction tube, how fast you add the solvent, how exactly you do, how much vacuum you put, too much, too little, does it go evenly, nicely? Now you put your sample. So there are all those small nuances which are even difficult to explain, such as filtering something. How even is this layer here on this filter? Maybe it's not so even. You still get the result. It's not a blunder. Yeah, but not as good as it is with a completely skillful person. I will teach you that later. It is. Interestingly, very interestingly, even blunders can be evaluated. Although it's not really a good thing, but and not so straightforward. But yes, we will see later on all those things how we do. And the how well you do. I can actually even give you one very simple example right away, just so that I would not only refer to the future, but would maybe give more information today. If we speak of sample preparation for trace analysis, then I think most of you agree that one of the key parameters, how well you do that, is recovery, sample preparation recovery. Recovery is a tricky quantity. It actually accounts for also other things besides sample preparation, but sample preparation oftentimes is the main one. That recovery, or perhaps expressed as biased, is also mathematical nuance. Let's not get distracted. That recovery can be included into uncertainty calculation, as I will explain you later on. And now, if you have two workers, one gets constantly recovers 92%, 96%, 88%, 92%, and the other one is constantly getting recovery 77%, 72%, 86%, 81%, etc. Probably the first one is doing something better so that less analyte gets lost. And it does not mean that the second one is like on the floor or on the bench or breaking glass. That's not the issue. Simply the manipulations that the second person does are maybe not so good, maybe not stirring enough. Maybe some sludge was somewhere on the wall. Person did not really stir it like this. So that part, the analyte from that sludge did not get extracted. So there are, again, everybody who has done such analysis, I think you can think of numerous kinds of small nuances that can influence. Did I manage to? Okay. Oh yeah, okay. The cubic is close enough, close enough. Yeah. If you speak from 1.5 meters of the cubic, then it's fine. Oh, wait a minute. Wait. Oh. Let me do a small intermezzo. When you are talking, watch this Evo up there, and now watch. If you look at the icon besides Evo, you see the icon is like doing something like this, yeah? Oh, when it is doing like this and Evo is written up there, it means that the system is hearing. But now let's be quiet. Nazi disappeared, and the icon is not doing it. This is how you can determine whether the microphone is working well. Now the microphone is certainly working. Yeah, you see the icon is like inflating and contracting, and Evo is also written. So try now.
No, I think it goes. Because my question goes like just to reassure that I understood. When we need to present our uncertainty, we use better the relative uncertainty when we need to for it not to variate too much from the value. Like because the absolute is going to vary proportional to the value that we have, but the relative one is the one that is usually doesn't vary too much, right?
Correct.
So if we had like a big relative uncertainty, like in the example that it was before, can we somehow assess the work an analytical lab has done if they have like a really big relative uncertainty? Because that means that the certainty will be like close to the value that we had, and I don't know if some lab has a big relative uncertainty, will mean that the analytical methods applied was not good, or they need to like improve how they make the analysis.
I'm not sure I fully understood, but yes, if a lab discovers that the uncertainty is very big, so that the uncertainty is so big that it is not possible to give the, let's say, to make the decisions or to answer the questions for which the analysis was carried out, then yes, they have to do something. It is most important, and perhaps I even should actually make even a better slide. But in principle, this slide here tries to convey it. How small uncertainty you need depends on what decision you want to take on the basis of the measurement. Or to put it even more like correctly, what decision your customer wants to take on the basis of the result. Very often the analytical chemistry lab people just get samples, they do the analysis, they give the results. Somebody else makes all the decisions and uses those results. So if for them, for their purposes, the uncertainty is too big, then yes, you should do something. Otherwise you will lose the customers. I don't know, did I get your question right?
Yeah, like my point is like, for example, in here we have 75%. That is like really high relative uncertainty. And without taking into account if the customer accepts, so it's good. But for like a personal assessment of my work that I'm doing in the lab, is that I'm doing a bad work? It doesn't matter if I have a relative uncertainty so high, like 75%.
Okay, yeah. Again, you cannot separate the level of uncertainty from the type of work that you are doing. For example, if it's simple acid-base titration and your aim is to determine the concentration of hydrochloric acid by titrating with sodium hydroxide and your relative uncertainty is 75%, you're certainly doing something wrong. Yeah, it's really not okay. But in some cases, when it's really difficult, very nasty analyte, maybe unstable analyte, very nasty matrix such as soil and extremely low levels, then you might end up in a situation when 75% uncertainty is pretty good. And maybe you only need to know the order of magnitude, like here. This is the question here also is in a way right now in the order of magnitude. These are roughly 10 times different. And just to saying whether it's 10 times bigger or 10 times smaller, for that purpose, this uncertainty is okay. Otherwise, or let me give another answer to you. If you are getting this kind of result, but then your friend is getting 0.8 plus minus 0.2, the other friend is 0.8 plus minus 0.1, maybe your idea was that, okay, can different analysts be like assessed that, okay, your uncertainty is so big, you are not so good, but your uncertainty is very small, yeah, you are very, very good. I would say sort of. I'm not aware that anybody is doing that anywhere like that. And also uncertainty evaluation is, I mean, it also depends on what is the approach that you are using. As we see later on, for the same analytical result, uncertainties obtained by two different ways can be different. They can be significant. And it is not clear if one or the other is wrong. They might be both correct in the sense that they both express doubt, as we explained last. They both express doubt, and simply in one case we had more information, so we were able to get narrower answers. In the other case, we had less information, so our doubt remained bigger. Yeah, I'm still not sure if I managed to answer you, but I tried.
It's okay now. I understood.
In any case, yes, perhaps the biggest thing is, if you do some simple titration, your expanded uncertainty should be few percent or even less than that. In some higher level alloys, where amounts of elements have to be in very accurate ratios, also some even 0.something% relative uncertainty for 1 or 2 might be like suitable or might be required. And then on the other hand, other end of the scale, yeah, there's some trace contaminant in meat, in soil, I don't know, in sewage sludge, in ocean, yeah. Trace contaminants at very low levels, yeah, very difficult to separate. Then uncertainties tens of percent, and in some cases many tens of percent, something like 50, 60, 70 might be the best that we can get. Okay, let's then move on. All right, then now uncertainty sources. Wait a minute. Elvin is also asking. Professor, one recover 70. Elvin, yes, it can be systematic error from one analyst, which might lead to the analysis of that analyst being of higher uncertainty. Yes, yeah. Less accurate. Yeah. Or are they both valid and contribute to the whole uncertainty for that? You see, I'm reluctant to say that there is something called whole uncertainty of the lab. Obviously, if different people do different work, they might have different uncertainties. True, as we see later on, in the Nordtest approach to measurement uncertainties, we can also incorporate like several people into the overall uncertainty estimate of the method. But then it's still not the overall uncertainty of the lab. It's still for one method. And if both of these people do the analysis, then yes, we have to incorporate both of those. But it can be that the 70% is because of a blunder. It cannot be ruled out. Yeah, maybe that person is doing something wrong. Maybe not shaking long enough, or maybe not heating long enough, or maybe heating too long. Heating always too long because it likes to work like this. Okay, I put it to heat. Now I go to lunch. Yeah, the method says I should heat for 30 minutes. Yeah, my lunch usually is something like 50 minutes, but that's okay. Yeah, I'm heating longer. But maybe that analyte is a delicate one, so that it decomposes if it's heated. Yeah, and that one person often loses part because of decomposition or volatilization, something volatilized, or polymerizes. Yeah, and then precipitates out. Yeah, then it's not in the solution anymore. Then that could be considered a blunder because the person does something like explicitly wrong. But just by the numbers of the uncertainties, we cannot say whether there is a blunder, so that something was concretely ignored, or it's simple minor nuances that lead to this. This also ties well with the method property, which is called robustness or ruggedness, which is a property of a method which characterizes how easy it is to carry it out in such a way that you don't need extreme skill with your manipulation. You can do very normal movements that any human being can do and still get the good result. So yeah, there's a term, ruggedness or robustness. They have slightly different meaning, but broad term, they are the same. We will come to them later on in the validation part. Okay, now uncertainty. Yeah, uncertainty sources. As I said already, I think last time, one of the most important skills that you hopefully get from this course is that you have in your head some kind of list. What possible uncertainty sources might influence your method? Whenever you do some method in your lab, then you think about all of them. Okay, can that be an important one? Probably not. Can that be? Oh yeah, that can be an important. Let me see how I'm doing so that this uncertainty would be as small. And we now now we'll try to give you still during today, and we will probably not finish this today, an overview of the typical uncertainty sources in chemistry. It's not all that possibly you can imagine, but still a very large majority is. Uncertainty source is a concrete reason for existence of an uncertainty contribution. So something that causes uncertainty. And you have to consider all the uncertainty sources. Yeah. As I said, this is a very important ability of an analytical chemist. And how to, I have a typo, how to minimize their influence also you should know, or this is also an important part of analytical chemistry education. And at least to some extent, I also in this course will teach you this minimization thing. Yeah? But that, of course, secondly comes in the lab, which most of you are attending already now, and then you will be attending throughout the course. I'll correct the typo. And now what also I think I already said on one of the previous lectures, although you should consider all important or all uncertainty sources, and those that are important you should take into account, but this does not mean you should quantify all of them individually. You can quantify them in big batches. And we will see later on with this NORTEST approach that actually there are only like 2 or 3 batches, depending on how you count, which account for all the different uncertainties. That's something we will come to later. First uncertainty source that I'm presenting here, if we start from the very beginning, is sampling. And in sampling, it is like the first or the key thing is that sample might be to some extent non-representative. Out of curiosity, I guess you probably know, but still, please raise your hand who understands what sample representativeness means, what it means that sample must be representative. Okay, people on the internet, who thinks that understands what it means if I say this sample is representative? Some people not. Okay, but then let me ask differently. Who feels uncomfortable when I say sample representativeness? Who would like an additional explanation? Nobody wants. Okay, then yeah, leave it at that. That we consider that you all know. So, sample representativeness is typically not such a big problem if you analyze something which is homogeneous. So that if you have a big bulk of something, then from any point of that bulk where you take your sample, you get pretty much the same thing. Drinking water is a good example. Yeah? It's not bulk in the sense that you are not standing in front of a cubic meter of water, but if you let the water run from the tap, you discard the first part, what comes out, then what comes out of your tap thereafter is pretty much the same. It's pretty homogeneous. Drinking water is good. Also, if you analyze some kind of, let's say, soft drinks, yeah, and there's a huge, like a lot of soft drinks, many thousands of bottles, you take some random bottles, they probably pretty much reflect what the whole soft drink lot contains. But things are very different with these types of matrices: soil, fruit, sludge, semi-solid fuels, natural waters. Also, when I said soft drink, I meant soft drink. When I say orange juice, does that have any specific problem differently from soft drinks? Is additionally problematic with orange juice as compared to something like Fanta or Coca-Cola. Ja, Gleb?
Colloidal system, non-homogeneous.
Exactly.
Quite a lot of ways.
Exactly, yeah. Juice has the liquid part and the solid pulp that is floating around that can be settled. So if you just take juice, then the solid part is on the bottom. If you now just take a sample from the above, you get essentially non-representative sample in the sense that you're analyzing essentially just the dissolved matter. But whatever is attached to the solid particles, you don't analyze. In some cases, that might be the purpose. You want to analyze only the solid part. This is very much to the definition of the measurand, what exactly you want to measure. That is something we will also come to later on, and I will explain more. But typically, you would still be interested in determining some analyte content in the whole object, meaning in the case of juice, it would be both the liquid, the dissolved part, and also the non-dissolved, the other pulp part. The same goes with natural waters. For example, in this country, most, I don't mean seawater, I mean these lakes and rivers. Most lakes and rivers can have a lot of dissolved things and a lot of colloidal matter in them also. And if we speak, for example, about heavy metals, not all of them, but some of them, then there are a number of heavy metals that predominantly are adsorbed onto the colloidal particles and are not dissolved. So that if you only analyze the water the way it is without any of that colloidal matter, you get one result. If you include colloidal matter, you might get a significantly higher result. And heavy metals are not the only example. There are also other analytes that can be adsorbed onto this colloidal matter. And here again, it is very much about definition of the definition of the measurand. What exactly it is that you are measuring, either filtered water or not filtered water. Yeah? All these things must be considered. And even if you shake your orange juice before analysis, there's still some danger that the ratio of liquid and pulp in your sample is not exactly the same ratio as it was in the bottle. Now, orange juice is still a simple thing. If you now think of what is a soil, which contains all kinds of small wooden sticks, dry plant leaves, there's sand, there are small stones, etc. So many things. Dead insect bodies or remnants of something, yeah. And also, if your aim is to characterize the soil from some field, from some area, then part of the area might be drier, the other part might be like more moist, more wet, and immediately the consistency, the biochemistry of the soil also differs. So that to get a soil sample which still is representative of the whole area that you want to characterize is very tricky. Sampling is a big thing. For example, for sampling for environmental analysis, you have to have a license. I mean, you don't have to have if you just do this analysis for just like your own fun or for scientific research. But if you want to do that, again, in the framework of some legal acts or a legislature, you have to have a license. The same thing about sampling of water, for example. for environmental analysis so that environmental analysis can be really carried out to check compliance with legislation, then the person who takes samples must have license for taking it really needs education how to do correctly. And even if you do correctly, still, if one person takes soil samples from this field and then the other person does, if nobody does anything wrong, the average composition of those samples will still be slightly different, and the average composition will be slightly different from the average composition of the whole field, which means the sample will not be completely represented. Meaning the analyte content in your sample might eventually not be the same as the average analyte content in the whole object that you analyze. Please raise your hand who thinks that understood what this uncertainty source means. People on the internet? Elvin, Madis? This is very good. Okay, yeah, very good. And if you don't understand, immediately type here. Yeah, I will then see and reply. Now, the next interesting thing is that sampling uncertainty is not always necessary to be included into the uncertainty budget. What does that mean? If you are working in a lab, and now some customer brings you a sample and says, I'm interested in, I don't know, cobalt content in this sample, then you typically cannot take responsibility for how the customer took the sample, where is it taken from, etc. You can then only give the result for this sample. Okay, this sample has 20 milligrams per kilogram of cobalt, for example, whatever the result is. And you only look at the sample. So the sampling uncertainty in this case does not matter. If sample is brought to you and you are asked to measure the content of the analyte in the sample. But there's another possibility that you work in some, let's say, agrochemical laboratory, and you get contracted with some agrochemical firm who said, hey, we want all these our fields characterized in terms of how much phosphorus is in the field. And the lab is also tasked with taking samples. So if your lab then, or your lab people go that field and they take samples and bring back to the lab, and typically soil samples are very big, they are kilos, might be even tens of kilos. Then they are divided into smaller parts. There are certain devices that are used for that, so that to preserve the representativeness. If all that is done by the lab, and if the customer is not interested in any individual sample, but is interested in the bulk, in the big object, then typically the lab is required to give the result for the whole object. And then sampling uncertainty is part of the uncertainty. So it depends whether you report uncertainty for the sample or for the whole object. This can be very different. And sampling uncertainty can be one of the biggest uncertainty sources in the case of difficult situations, and soil analysis certainly counts as such a difficult situation. Please raise your hand who understood the logic that, okay, sampling uncertainty might not always be part of your uncertainty. Okay. Good. But, so outline the subsampling uncertainty always is part of your uncertainty. So the customer might have brought to you 1 kilo of soil. Okay, I need phosphorus content in this soil. There is 1 kilo. but your device actually, or your sampling device can work with maybe 15 grams of soil. You cannot use more. Now you have to take from that 1 kilo sample a subsample of 15 grams. That also has to be done in a representative way so that the relative content in 15 grams is the same as the relative content in 1 kilo. And that is completely on you. That uncertainty you have to include, and that is something you are responsible for. Again, there are special, I think quite probably explained, those of you who took the practical chemical analysis, quite probably explained to you that there's special devices for dividing samples into small parts. Yeah, you pour into something which then divides differently and so on and so forth. So that first you need to homogenize that 1 kilo, then you put it into that machine which divides it into maybe 4 parts. You take one of those 4 and divide again, and finally you end up with some quite small sample. And that uncertainty due to subsampling, you really need to take into account. We will come to that. Okay, sampling uncertainty is not very big part of this course because most of the time laboratories work with samples that were brought to the laboratory. They don't take samples themselves. But now, any ideas how would you take into account subsampling uncertainty? Any ideas? Anything? We will come to examples later on, but already now it's not really bad to think about it. How would you take into account subsampling uncertainty? Leeb is laughing. So simple question that makes you laugh. Okay, let's see. It's a very simple answer, by the way. I would not be asking otherwise if it would be some sophisticated math or something. No, it's a very simple thing. Perfect. Exactly. You don't take one subsample, you take 5. And you analyze all 5, you see how much they differ. So obviously, if they differ a lot, might be not so good. And you can present to the customer the average value, yeah? And then you also can use these differences in your uncertainty budget so that you can get how much uncertainty comes from that. But let me now ask, this is very nicely answered, but let me now ask again, okay, the standard deviation between the results that you got from with the 5 subsamples certainly does characterize subsampling uncertainty, but is it only subsampling uncertainty, or is there something else also involved there? Yeah, is the mic? Okay. For some reason, we have all the time problems with microphones. So I'm sure people on the internet.
So I think the uncertainty is not just associated with some sampling because it can be different when you do things in different conditions, or maybe it's different skills, or maybe different persons doing the subsampling. So that random effects that
Indeed, the standard deviation of values that you get from those subsamples, of course, does include subsampling uncertainty, but it also, as you corrected, includes all other random effects that affect your analysis. And here already we are coming to the thing that I already mentioned. You are not necessarily required to separate strictly, okay, this variability comes from subsampling and this comes from something else. You may want to do that, but this is not the strict requirement. If you can manage to evaluate your uncertainty as big batches, that's perfectly okay. So that in many cases, people probably would not try to separate, although that separation is possible. You can separate out how much variability comes from subsampling and how much variability comes from the other analytical part. Can anybody guess how? I'm slightly running ahead of things. Yeah, we are not yet where the calculations are, but asking such questions, I hope keeps it like more lively and gives you the possibility to think about things. So how could we separate how much variability comes from subsampling, how much from other things? Komal? What could one do? Find out. Ah, is any cubic anywhere?
That's like certainty and like in case with random error, and in case before we can like do it 5.
I'm not sure I completely understood, but I think there can be a much simpler answer, certainly.
I mean, like make one person like do everything at the same timing.
Yeah, no, I'm not speaking at the moment how to minimize, although that's extremely important. Yes, we first of all always should minimize variabilities. Yeah, that's the most important. But suppose now I'm the only person, so we cannot do, there's no other person. I'm only doing the analysis. What can I do to learn how much variability is brought in from my subsampling activity, how much variability is brought in from all the other manipulations that I do? No. Blanks are extremely useful and we will come to them, but not in this case, not so much.
As possible, one way try to measure of our method, trying to minimize as much variations that can result from the manipulation of my sample, in order to like to know that the only variability is part of the matrix.
Elvin, let's see. Okay, Elvin, you essentially answered the question. Elvin, I would not, in this case, as you write, I would not use the word uncertainty, but rather variability or standard deviation. Otherwise, what I think you see what Elvin is suggesting. You have those several subsamples, you analyze those subsamples, yeah, and you get their standard deviation. That standard deviation has all the variability due to subsampling and due to the analytical procedure. And then you take one individual subsample and do several analyses with that one. And that standard deviation gives you just the analytical variability. You cannot always do that though. Because sometimes you use up all your subsample with the analysis, then you cannot. Yeah? But sometimes you can, then you can. Please raise your hand who understood this logic. So that in one case, all variabilities will be included. In the other case, only variabilities due to your analysis. Yeah. And also what is interesting thing, let me specifically point out this last sentence. This here was added specifically for the Lyon study track of the EACH program. Online analysis or inline analysis, which works directly on the stream of product flowing somewhere or in reactor, yeah? That one tends to have, if all is done well, negligible or very low non-representativeness uncertainty. This is because in such analysis, you constantly see the whole stream of samples. And also in such analysis, people typically define the sample as the part of a material that is in contact with the sensing element. And as each program students have of course heard from several people, including during the winter school, this online analysis is something really big in chemical industry. Now, the next thing is sample preparation. Here again, we come to the issues that are caused with inhomogeneous samples. Again, drinking water is homogeneous, soil is inhomogeneous, orange juice also inhomogeneous. Yeah. And sample inhomogeneity is always an issue. And this is actually in a rather big overlap with sample non-representative. So when we speak of sample inhomogeneity and then sample non-representatives, these are like closely overlapping things. And sample inhomogeneity, effect of sample inhomogeneity and subsampling uncertainty are oftentimes the same thing. Perhaps I even will write here. Wow. This sample uncertainty due to sample inhomogeneity is often the same thing as subsampling uncertainty. It leads to the same effect. Okay, I have 1 kilo of sample. Now I need 15 grams for the analysis. I somehow managed to divide it. Yeah, so now I have several portions of 15 grams, and now I'm using them for the analysis, but they are not exactly of the same composition as that 1 kilo was. Again, if you take 1 kilo of drinking water from this tap, then this uncertainty essentially does not exist, because you take it like this and it's done. Yeah, it's okay. If you take 1 kilo or 1 liter of orange juice and you shake well, then again, subsampling uncertainty or sampling homogeneity uncertainty, very small actually. Probably not really a big issue, but 1 kilo of soil is a completely different matter. 1 kilo of meat is a different. 1 kilo of many things is. Of course, what people do with meat, fruit, and essentially any kind of any kind of food, they have a blenders. Put all those things to a blender, which is essentially the similar blender as you may have in your kitchen, yeah, which makes a slurry out of that. Yeah? So that with oranges and with meat, you can do that, but with soil, it's not so easy actually. Soil is oftentimes quite corrupt, like abrasive. It has sand and things, and so people typically don't put soil into such blenders. They typically do it in some different way. Okay. Then in homogeneity, then the next thing is that it can oftentimes be very difficult to completely separate your analyte from the sample. Let me perhaps even take one step back at the moment. If we speak about now in very, very general terms, okay, I have some kind of matrix, I have some kinds of analytes. And suppose they are at low level, so it's not major components. We are still chasing some contaminants or something like that. What are in very big terms, in very broad terms, two approaches, how you can approach this question? How do I get my analyte out of my sample? There are, in very broad terms, two big approaches, which are both widely used. Two big ways. Hint, those of you who were in atomic spectroscopy, you exactly. Option number one, you digest, you essentially destroy the matrix. And extraction, beautiful, yes. Two ways, you either destroy the matrix so that the analyte remains completely is dissolved and remains in solution, or somehow you try to extract the analyte out. Destruction of the matrix, of course, is simpler, and you don't have destruction, but can we always apply it? Not really, yeah, because your analyte gets destroyed also, yeah. So again, it's very simplified, but in very broad terms for inorganic and for elements, we destroy the matrix, yeah, and then we analyze. But for organic contaminants, such as pesticides, we have to extract. And this, of course, also leads to the situation that oftentimes inorganic, or again, let's put it, elements can be obtained with higher recoveries, and you can get them easier because nothing remains in the matrix because there remains no matrix. Yeah, everything is done well. Yeah, but now extracting is also always tricky because the analytes want to stick with the matrix. They don't want to come. Yeah, they want to stay there, and then you have to. And of course, it all is especially problematic if it's low levels. If the matrix is difficult, I'll come to that in a moment, and if the properties of your analyte are similar to the properties of your matrix. And yeah, I've already given all kinds of examples, but yeah, for example, pesticides in fruit, pesticides in cereal. Typical example of nasty kind of extraction, which does not have 100% recovery, oftentimes has recovered something, maybe 85%, maybe 77%, maybe 92%, yeah, depending on the situation. And yeah, can be true. And now, when I said with previous slide that sampling can be the biggest uncertainty source, this is perfectly true also for sample preparation. And besides being often the most important uncertainty source, it unfortunately tends to be also difficult to quantify and difficult to take in. We will come to that later on. So I would say that in many, again, I need to choose my words carefully here in order not to direct you to sloppy working practices. But in many cases of such really difficult analysis, such as trace pesticides and natural matrix, all such things as balances and pipettes, etc., can be considered as essentially having zero uncertainty. Because you can pipette, for example, 10 milliliters with very high accuracy compared to extracting some tiny traces from some nasty sludge or nasty soil or something. This does not mean that you need to disregard volumetric wear. No, you still have to take it into account. But this simply means that usually the effort should be put first of all into sample prep. There are other nasty uncertainty sources. We will come later on, maybe not today, but later on when we come to selectivity, interfering effects and things. Those are very nasty. Now, difficult matrix. I've said here numerous times, difficult matrix. More or less, you already know what it means. But now, I have hidden some text behind this blue thing. And now it's over to you. Please now tell me what properties of a matrix make it difficult. A number of those I've already said here, or you already. I will then try to write these. So, what makes a matrix difficult? If it's not homogeneous, okay, perhaps I'll put that. You see, in some cases, solid matrix can be not too bad. If it's some like metal alloy, for example, which is essentially homogeneous thing, but inhomogeneity is possibly the first thing. And perhaps I will put here in parentheses solid. Because here you, Gleb, are perfectly right. Liquids are usually still better than solids. Okay, inhomogeneous, solid. What else? But what are those things that cause interferences?
Maybe the ones that have similar response than the analyte.
Okay. I'm trying to. So the matrix then contains components that are similar to the analyte. Okay. Matrix is similar to the analyte. I will put here. But now, let us dwell on these interferences for slightly longer. For the good, how to guide you. So, besides that matrix contains components that are similar to the analyte, what else might make matrix especially bad from the point of view of having interferences? I'm asking very vaguely. I hope that maybe somebody can say the thing. Sorry? Yes, that is a very good point, by the way. Yeah. Very good point. But there's something more. Let me try to think. Out, I'm not so good at examples. Yeah. Yeah, Elvin, yes, matrix generating strong signals. It is quite a bit like this one. But there's something else. Come on. Possibly, but you see, this is actually already, this answer actually is already contained in this thing. Many components. So in some matrix, there are simply not so many different compounds. So interferences are not so likely, but in some matrix, there's a huge number of everything. And that, in such a case, interferences is much more likely. Yeah? Many components. Like again, metal alloy might be just of two metals. Yeah, it's okay, it's solid. Yeah, not too bad. Yeah, but then you might have some metal ore, which contains God knows what. Yeah, all kinds of different minerals and things, which might be a lot more problematic. There are many components. Now, let me also. This maybe is too obvious, but still, when I said previously that, okay, yeah, there are two options. We either destroy the matrix or we extract. And there's actually a third option also, which we cannot always or cannot so often use, but still sometimes we do. Can anybody guess what else we can do? I brought an example today, actually, or several examples today of that kind of matrix. We don't really destroy it, and we also don't extract. We do a third thing. Not really, yeah. No, not exactly. In principle, you are close. We dissolve it. Some samples can simply be dissolved, and that's a very nice thing because you don't destroy it. Your organic analytes do not get destroyed with that. Yeah? And the examples that I brought are soft drinks, for example. You can dissolve them in water and dilute them, and there you go. There are also other things that can be dissolved. For example, let's say maybe some industrial chemicals, then maybe honey, for example. Honey is actually a very tricky thing, but honey can be dissolved in water, which is a good thing. Yeah? So that matrix is nasty also if it cannot be dissolved. I would say most of them cannot. You cannot really dissolve meat. You cannot dissolve cereals. You cannot dissolve soil. You cannot really dissolve most of the things. But sometimes you are lucky and you can dissolve. I think we actually, we've done pretty good job already. Perhaps I will just put in one more thing, which is like tricky and it's not very, very clear if it always is really a problem, but it actually is nasty if the matrix is unstable. So that some processes take. Golam is saying that, by the way. Oh, very good. Yeah. Golam said it before I start saying. Yeah. Unstable. Now let me see. I have one list here. Cannot be solved. Strong. Aha, okay. Yeah, we have one more. Yeah. Sorry, Hamdi. What did you want? Sometimes it does not, because sometimes it actually does not matter if some other matrix component is decomposes or not. But sometimes it can, for example, some matrix component decomposes, and then what happens is that the analyte is then kept more strongly in the matrix. And you don't know that, you count that, okay, you can store it, but then it decomposes and the analyte is stuck in there, and then you are. So let me now show what I had originally here. We see that we actually have all this, and we have even one more, which is that matrix holds the analyte strongly, which I think was written. But matrix holds analyte strongly is to some extent covered by this, but not fully. So that it's good that we have that additional thing. And here are some examples, but I've already brought them to you many times. And seawater and orange juice, we've already discussed orange juice and found out that it's a inhomogeneous matrix, although still not as nasty as soil, perhaps. But what about seawater? Seawater is pretty homogeneous. Actually, in most cases, we can say that suspended matter is so little that it doesn't really. Is it a good matrix or not compared to drinking water? Not good. What's wrong with seawater? Lots of components, but anything else? Huh? Yep. Seawater is tricky in some special way. It has high salt content, especially high chloride content. That interferes with a number of techniques. Very importantly, for example, ICP-MS, which is the typical trace element technique, seawater is a bad matrix. And you need to dilute, and then of course you lose these beautiful limits of detection, yeah, because they go higher, because whenever you dilute by 10 times, you lose 10 times of your limit of detection. But if you need to dilute even more, then you. Okay, I think we sorted out more or less what difficult matrix means. So let's continue. Yeah. Yeah. Please, yes.
Just like if we define our analyte, everything that other compounds that are present in our matrix are known as interference compounds, or you can say that other different compounds that can be there are interference, or they are just they interact.
They are interference when they interact with analyte, so that they do something to the analyte, or with the technique. For example, they give peaks somewhere where you expect that the analyte peak is here, but the interference that gives it. Otherwise, if a component does not do anything like that, it's not considered interference. For example, if you do trace element determination in drinking water, then water is the main component of drinking water. Nobody would say that water is an interferent. That's how. Did I answer? Into which category? Unstable. You mean which radioactive undergo radioactive decay? I think they do, but you see, anything related to radioactivity is quite far from my competence domain. Yeah, so that working with radioactive samples or determining radionuclides, it's a completely like separated, very important, but still separate topic of analytical chemistry. I'm not really able to say much about that. But temperature-sensitive compounds, yes, they are tricky, yes. And you encounter quite some of them in all kinds of biomedical and biomolecular analysis. A number of important like biomediators, etc., which work inside your body might at the same time be quite unstable outside body and not so easy. So now here comes an example about a similarity between matrix and aniline. And there are two pesticides here. And this is very interesting because those two pesticides are both very well known and very prominent. So DDT used to be in the past the most used pesticide in the world. It is actually very efficient and it has very low acute toxicity to humans. So it's interesting. Such strange chloral compound, doesn't really. Not really very harmful to humans, but it turned out that it's extremely harmful to birds because their eggs are not solid. So they cannot reproduce nicely. So that extensive use of DDT led to decline of certain bird species. So it's now forbidden in many places, in most places, I would say, certainly in this country and in the European Union. Although in some very special situations, DDT might be used even these days. For example, if like some refugee camps and you really need to kill insects, then in such places, because of its cheapness and high efficiency, still might, but very rare. And then glyphosate is the most used pesticide in the world right now. They are true, they are different. This is an insecticide. So DDT is an insecticide, kills insects. And glyphosate is herbicide, meaning it kills plants, it kills weeds. Glyphosate also has quite low acute toxicity, but now they are finding that it does possibly have some carcinogenicity, so that it is still allowed in the European Union, but there are strong voices against it, and maybe it will be banned soon. Who knows? But they are very different by their properties. And now, who knows what this thing is? Who does not know what this thing is? Okay, many of you. This is log P, or logarithm of octanol water partition coefficient. So if you take some compound and make the biphasic system water and octanol is a long chain alcohol. Now you put that compound in, irrespective whether you put it into the aqueous phase or octanol phase, and now you shake very vigorously and for a long time, and now you let it settle. And then you measure concentrations in octanol and in water, and then you take the ratio of the concentrations and take logarithm of that ratio. I'm explaining in simplified terms now. It's a somewhat more sophisticated thing if it is ionizable compound, but let's leave that aside for a moment, just to give you the very general idea. So log P value, sometimes it's also termed log POW, sometimes small o and some more w is here. So to specifically say that it's octanol water partition coefficient. Although if it is given without any subscripts, then almost always people interpret as octanol water partition coefficient. This is the main parameter for characterizing lipophilicity of lipophilicity means that if some compound gets into your body, whether it will now be in the aqueous phase in your body or in lipids, in fats, the higher is this value, the more it concentrates in fats. The lower is this value, the more it concentrates in water. And log P above 5 means that the partition coefficient is above what? Oh, yes, it's also above 10,000, but above something else also. Your answer was technically correct. What is the number of which we take logarithm, decadic logarithm, and we get 5? 10,000 would give us 4. 10.5. Yeah, and that means 100,000. Yes, but yes, Gleb, you were technically correct, because whatever is bigger than 100,000 is also bigger than 10,000. So I cannot say you that you answered incorrectly. Yeah? Yeah, it's so tricky. Yeah? If it's not equal, then you must be very careful with saying that somebody said something wrong. Yeah? Okay, in any case, as you see, the concentration ratio is more than 100,000, so it's heavily concentrated in the lipid phase. And here it's negative. And negative below 0 means that concentration in water is higher than concentration in the lipid phase. Because whenever we have a positive number which is below what? Okay, let me not. Whenever we have a positive number which is below 1, our logarithm is below 0. Now, this is here to compare the properties of the compounds with the properties of the matrix, which in this case is a fruit matrix. What is your opinion? Is a fruit matrix a polar water-rich matrix or non-polar lipophilic matrix? Polar, a little bit polar or very polar? Yes, this is very well said. Almost as polar as you can get. It's very polar. If you think of something like an orange, it's essentially water. Whatever is in there is sugars, acids, which are all very hydrophilic compounds. There's almost no fat in orange at all. The only fruit of having any really significant amount of fat is, at least in this country. In your countries there might be more, but it does not grow in this country. But avocado, yes. Avocado is famous for being a fat-containing fruit. Yeah, most other fruits don't. But again, I must be very careful with my words, because I guess in some of your countries you might have many times more different fruits than what we have on sale here. So you might have in your country some fruits which are also fat-rich and are not avocados, which I maybe even don't know the names of. And just to be exact, avocado does not grow here. It is imported from the south. Okay, in any case, fruit matrix, very polar. And what happens now is that this one, because of its high lipophilicity, is very nicely extractable into all kinds of non-polar solvents or into C18 solid phase extraction. And when you want to get it out of fruit matrix, it gives you reasonable recovery, or even very good. But this one, because it's so similar to the matrix, because it is highly hydrophilic compounds because of this minus sign, this minus sign, this plus sign, and this minus sign. You see, it's a Zwitter ionic, etc. compound that actually has 2 minus signs. And you may well know that ionic compounds are extremely hydrophilic. It also can be protonated on these sites, but the way I've drawn it here corresponds to what is the most abundant species at roughly neutral pH. So at neutral pH, it's mostly dianion, and therefore very hydrophilic. It is very poorly extracted from water. essentially you want to or try to extract with this fruit matrix using water, which is in itself a very nasty thing to do because fruit matrix already is mostly water. So it's like partly you sort of dissolve what is in that fruit matrix and partly you extract, which also means that all the sugars and acids and things that are in the fruit matrix also come into your extract and will interfere possibly later on in the analysis. And then the other thing that people do is this here. SAX means strong anion exchanger. Strong anion exchanging solid phase extraction is another way of how do you do sample preparation for this one. And in any case, you typically end up with poor recoveries, and people in pesticide community oftentimes say that this is the nastiest pesticide to determine in, let's say, everyday analysis because of its properties, which are very similar to water. Oh, sorry, not similar to water, but which are very, very hydrophilic. And I think I don't actually need to repeat this. This already, or I don't even need to ask this. I actually explained all. It is good if analyte's polarity is different from matrix polarity, or in other words, if analyte's properties differ from matrix properties, then you can extract better than if they are very. Any questions here? Okay, if not, let's look here. You might say, hey, wait a minute, okay, low recovery, so what? We can determine recovery, and correct. Yeah, so that even if our glyphosate extraction recovery maybe is only 50%, 50, which is very bad actually. But why not correct? We essentially multiply all our results by 2, yeah? If you think then if your recovery is 50% and you want to correct, you divide by 0.5 or you multiply by 2. So we multiply all our results by 2 and that's it, done. Yeah, so we don't need to worry about our poor recovery. But what happens and what is actually a very general thing, the worse is the recovery or the lower is the recovery, then the worse is the sample preparation reproducibility. Meaning, you might get now 50% recovery, but next time you get 30%, then you get 65, then you get 28, then 31, then 26. So that if you correct, okay, yeah, somewhat better, but you will still have enormous variability and still high uncertainty. So that besides other recovery correction problems, we will come to. I have a special section in this course later on when I discuss with you when is it reasonable to correct for recovery and when it's not reasonable, rather you increase your uncertainty. So even leaving that aside, when recovery is low, your uncertainty will typically. And if you have some trace analysis and you have low recovery, then one of the first things you should do with your method is to improve that. Sometimes people ask, okay, yeah, but what is a suitable recovery? I would say everything above 90% is certainly okay. I would say most of the time above 80 is also fine. Now, at least in some guideline materials, it stands that 75 is a kind of a borderline. Below that is sort of not really acceptable. But for glyphosate, certainly exceptions are needed because with glyphosate, it can be lower. And with some other analyte possibly also. All right, it's 11:45. Yeah, we have reached the end of today's lecture, but we still have time for questions if there are any. Play, yeah. I think somebody asked that already last time, but or something similar. But let me then answer. There are different ways of which the two most common are spiking. So that you take your matrix and you spike. You know how much you added, and now you do all your sample preparation. See how much. And the second is certified reference materials. That you buy a certified reference material. Of course, you don't always find a certified reference material on sale. That's a separate problem. But in principle, these two are the main ways. Spiking has its own problems, of course, and I will explain them later on. But in principle, this is how you do. Yes, either of those or possibly something else. There are actually more possibilities. Perhaps let me not get too deep. But yes, in trace analysis, recovery determination is almost always necessary. You almost always should characterize your method with recovery. Even if you don't correct, you should still have it. Yeah, could you take some of the instruments?
It's sample preparation as uncertainty sources said that most important, right? But there are methods that deemed or claimed to be without sample preparations. Does it mean that we don't have to take account for their uncertainties? For example, the direct analysis of mercury is just what you do is you take subsampling, you put it in the machine, and you didn't do any sort of sample preparation.
Yeah, I would say this is actually more a language question than anything else. You need to take into account all the uncertainties that are in your method. And if there are some manipulations which perhaps are not called sample preparation, but can still introduce uncertainty, they need to be taken, or the respective uncertainty needs to be taken. But true, there are chemical analysis where there's no such thing as sample preparation uncertainty, such as titration, determining hydrochloric acid concentration with titrating with sodium hydroxide solution. Obviously, there's no such thing as sample preparation there. Also, I would say, if you do, for example, again, if we take this drinking water and you do, for example, sodium or potassium determination with ion selective electrode, you simply take the water, here's the water, you put the electrode in. Maybe you have to put some conditioning buffer or something. Put the electrode in and you take the reading and calculate the result. There's no sample preparation. Yeah. So yes, there are such cases. And also, this one here, again, online analysis, is also one of those where you typically never can do any sample. Typically looks like this. There's a reactor. Inside there's some optical probe. Some liquid or slurry or whatever is mixing in the reactor. Whatever touches your probe is your sample. And you cannot get into the reactor, and you don't want to get into the reactor to do any sample preparation. You simply use the optical information that is transferred to some device, and you base your decisions on that. So in that case also, you don't have any sample preparation and no sample preparation uncertainty, but you of course have uncertainties due to other kind of things, such as, for example, insufficient selectivity of that particular probe. which we come to hopefully in the next time. Did I answer? No. Okay. Tomorrow we will continue with these things. And since I still have quite some places where I want to discuss, yeah, so we go slowly. So probably we will not yet finish this part tomorrow. But if it happens that we will, then uncertainty part 2 is already on Moodle. You can it is already updated, yeah, and you can already get it from Moodle. And hopefully next week we will start with uncertainty part 2. But tomorrow probably we will not yet start. So we will probably still take time for these slides. But for today, thank you, and lecture is over.